This class, no one is coming for offline. Okay. Bharat, what happened? Bharat?
ऑफलाइन हो रहा है
बिल्कुल हो रहा है यार, रोज ही होता है, मतलब फिजिक्स तो रोज ही होता है. Maths and chemistry is on Monday, Wednesday, Friday as of now. So moving on, galvanometer conversion into a meter and voltmeter. That part we are supposed to do probably, or we did. I think we started some portion. We did. Yes.
यस सर
We did a conversion of galvanometer into voltmeter and ammeter, and then we did some questions also. So I think that part is done. Now we have to start the next chapter. Anything left from last chapter? Anyone? कुछ न्यूमेरिकल्स हम कर रहे थे, वो न्यूमेरिकल्स आपको अभी करने हैं on your own. We'll discuss in the Friday class. Chapter number 5, magnetism and matter, and I asked you to revise this through the CBSE class lecture videos so that we can do it quickly. It's a mostly theoretical chapter, but now theoretical chapter has become kind of important because MCQs may be formed from that particular part. So in this chapter, we'll see the permanent magnetism, the magnetism which is existing without the current, or some specific materials have the magnetic property like magnetite ore of the iron and all. So we'll be seeing the permanent magnet or bar magnet. Permanent magnetism or permanent magnet. Magnet are also termed as magnetic dipoles since there is one north pole, another south pole, and it is separated by some distance here in this particular scenario. जो हमने last chapter में पढ़े थे, a current carrying coil behave as a magnetic dipole. It does not have two separate poles. It has north pole and south pole on the same loop. So permanent magnet में या magnetic dipole में we assume that there are two poles which are separated by some distance, exactly similar to like electric dipole has one positive charge, one negative charge separated by small distance. Now the question is, सबसे पहले the magnetic behavior was observed by. How was the behavior of magnetism in certain ore? It was discovered. The first, it was by the shepherds, those who have the iron nails in their shoes. They found difficulty in moving through a certain hilly region, and that particular place was island of Magnesia. So their shoe as well as their stick, which has a pointed nail at the end, was they found difficulty in walking or moving, and that was supposed to be because of that stone, that particular hill on which they were trying to move. So they used that stone, some piece, and tied it to the cork. And when floated on the water surface, it always pointed in north-south direction. And they started using it as a compass to determine the direction. That was the very first discovery of the permanent magnet or the bar magnet. So it was supposed to be some specific property which lodestone or magnetite Fe3O4 has. It attracts the iron pieces and some other more magnetic material. And another property is that it always point in a certain fixed direction, north-south direction. So the word lodestone, the name of that ore was lodestone, which is nothing but the iron ore Fe3O4, and also called as magnetite now. The name lodestone was because it was used for the leading the direction since it points in north and south direction. Anyway, so magnets now based on that particular magnetic composition of that material, we can design the artificial magnet by using some specific iron, cobalt, and nickel and magnetize it into a certain particular direction to a certain strength, called as bar magnet, artificial magnet, and based upon the shape. So first properties that they attract, second that they always, these are the very basic common properties जो आपने 9th में पढ़ रखी है, 10th में पढ़ रखी है, so that's why we don't have to write it. That they always like poles always repel, unlike pole attract, and magnet always point out in the north-south direction when it is released to free, when it is released to rotate, free to rotate, and it always attracts some magnetic material like iron, cobalt, nickel, and their alloys. Now, magnet always exists in the form of magnetic pole. Magnetic monopole is not possible. We cannot separate out this north pole and south pole. If we break from between, then another south pole and north pole will be formed along with that. So every magnet is termed as magnetic dipole. But जब हमने charges पढ़े थे, charges के electric dipole में, we say that it is the positive charge and negative charge separated by some distance. Here, north pole is considered to be a magnetic charge. Though there is nothing like magnetic charge, the better word is pole strength. QM is called magnetic charge, or which is also termed as the pole strength of the magnet. Pole strength को हम small m से denote करते हैं, which represent the same thing. और ये डिपेंड किस पे करता है? डिपेंड करता है काइंड ऑफ एरिया पे, कितने एरिया से वो मैग्नेटिक फील्ड लाइंस बाहर निकलती है. The distance between them is called geometrical length L, but magnetic length थोड़ी सी कम होती है. So the geometrical length is L, magnetic length ये poles exactly surface पर नहीं होते, थोड़े से अंदर होते हैं, but जब तक वो specify नहीं होंगे, we can take it as same as a geometrical length. So, like in the case of electric dipole, we had electric dipole moment as charge into distance. Similarly, in the case of bar magnet or magnetic dipole, उसकी strength को हम represent करते हैं magnetic dipole moment represent how strong that magnet is. How strong means how strongly the magnetic field will be produced. M, that will be defined as pole strength into distance or magnetic charge into distance. Right? L here is again the distance between the pole, which is actually magnetic length, but magnetic length is like 84% of geometric length. L is the distance between the pole. और जब हम किसी भी टेढ़े मेढ़े मैग्नेट को देखेंगे, any other curved shape magnet, then L will be the shortest distance between them. Now the magnetic field, why it is considered north pole to be positive charge? Because magnetic field line originate from the north pole, बाहर की तरफ north pole से. sorry, direction is opposite. The magnetic field start from the north pole and then it go toward the south pole. Outside the magnet north to south, inside the magnet is from south to north. So जैसे electric field line निकलती है positive charge से, magnetic field line निकल रही है north pole से, and that's why north pole is considered to be the positive charge. The pole strength of a magnet is defined as like the force that a unit pole would have experienced in external field. But वो again वो hypothetical है क्योंकि ऐसा कोई unit charge या unit pole होता नहीं. Magnetic dipole moment is similar to the electric dipole moment. Electric dipole moment में था charge into distance. So we can also write this as magnetic dipole moment as magnet. So हम इसके सारे फॉर्मूले कंपेयर करके इलेक्ट्रिक फील्ड जैसे ही बनाएंगे. The direction of electric dipole moment is from negative to positive, and for the magnet is from south pole to north pole. So the direction of magnetic dipole moment is from south pole to north pole. Direction of magnetic dipole moment is from south to north pole. क्या represent करता है इसकी SI unit क्या होगी जो हमने पहले निकाली थी वही होगी because formula was NIA. What is the SI unit, Bharat? What is the SI unit for the magnetic dipole moment?
Magnetic dipole moment का SI unit.
Yes.
SI unit is ampere square meter.
Ampere meter square. That's NIA. So IA is ampere, area is meter square. SI unit of magnetic dipole moment, which is the same dipole moment जो हमने पिछले चैप्टर में current carrying loop के लिए define किया था. So by that logic, SI unit of pole strength. Pole strength जिसको हम एक charge की जगह पे equivalent assume कर लेते हैं. Pole strength or magnetic charge, it will be ampere into meter because it is M into L. Right? Very good. SI unit of pole strength and magnetic charge is this. So any type of magnet, when the magnet shape changes, then L is the distance. अब L इसमें हम बात कर रहे थे magnetic length की. The magnetic length of a magnet is less than the geometrical length. Magnetic length is distance between the poles. Poles are slightly inside. Magnetic length is like 84% of geometrical length, 0.84. The north pole and south pole are slightly inside, so the ratio of magnetic length to geometrical length of a magnet. But हम इसको जब तक specify नहीं होगा हम इसको same ही लेंगे. The length which will be given, we consider that it is magnetic length is given. This ratio is 0.84. So when we have to find the field or when you have to calculate the force, we will just compare this with the electric field and electric force formula. Electric field के लिए it was 1 by 4 pi epsilon naught q by r square. Magnetic field के लिए it is mu naught by 4 pi q m by r square. Magnetic field is B is equal to mu naught by 4 pi. Electric field due to a charge particle, electric field was 1 by 4 pi epsilon naught q by r square. आइडेंटिकल इक्विवेलेंट फॉर्मूला 1 अपॉन 4 पाई एप्सिलॉन नॉट चेंज होता है म्यू नॉट बाई 4 पाई में. Q को हम लिख लेंगे QM by R square. हाइपोथेटिकल ड्यू टू मोनोपोल. Hmm. 1 by epsilon naught can be replaced by mu naught, and Q can be replaced by QM or M. To derive this is the equivalence. अब मैग्नेट के लिए जैसे इलेक्ट्रिक डाइपोल का कॉम्बिनेशन था वैसे मैग्नेट का भी कॉम्बिनेशन हो सकता है. अगर हम किसी मैग्नेटिक डाइपोल को या मैग्नेट को ब्रेक कर देते हैं, डिवाइड इनटू टू पीसेस. इफ यू कट इनटू टू पीसेस परपेंडिकुलर टू द लेंथ, क्या चेंज हुआ? दोनों के बीच की डिस्टेंस, दैट डिस्टेंस बिकम हाफ. एज अ रिजल्ट यहाँ पे बीच में एक नए पोल्स बन जाएंगे. सो इफ यू डिवाइड इनटू टू पीसेस, there will be two independent magnets will be formed, each have half the length. Pole strength will be same. Then length is half, magnetic dipole moment will also be reduced to half. M dash will be capital M by. Now अगर हम इसको लेंथ के along कट करते, if cut along the length divided into two pieces or divided into two part, so when we cut into two pieces, it will become M by 2 and M by 2. This total charge था QM minus QM. It will be divided into two pieces, QM by 2 and minus QM by 2. Charge half हो गया because area is half, and it will form again into two different magnets. Lengthwise same है, but pole strength reduces to half. So again, if dipole moment was M, the dipole moment become M by 2 and M by 2. परपेंडिकुलरली कट करेंगे टू पार्ट में तो हाफ हो जाएगा m by 2 और along the length कट करेंगे तो दो पार्ट में डिवाइड हो जाएगा again m by 2 accordingly there will be change. राइट ओके. सो ऐसे अगर हम दो डायपोल्स को कंबाइन करते हैं या दो मैग्नेट को आपस में कंबाइन कर देते हैं, two magnets of different dipole moment are combined together or joined together, tied together, welded together. Combination of two dipoles, which is nothing but combination of two magnets. M1 and M2 at an angle of theta. So हम ये दो मैग्नेट को हटा के इसकी जगह पे एक सिंगल मैग्नेट रख सकते हैं जिसका डाइपोल मोमेंट will be the resultant of these two. So net dipole moment will be root of M1 square plus M2 square plus 2 M1 M2 times cos theta. Right? So दोनों को हटा के हम एक सिंगल मैग्नेट रख देंगे and that will become a single magnetic dipole. By that we can find out the overall magnetic field. दो या दो से ज्यादा भी मैग्नेट हो, we can find out its magnetic field by using an equivalent dipole moment. Now suppose if you have to calculate the force between the two magnets. एक तो फॉर्मूला हमने कुछ किया था पहले किसका, इलेक्ट्रिक डाइपोल में दो इलेक्ट्रिक डाइपोल के बीच का फॉर्मूला, फोर्स का फॉर्मूला, इट वाज 6k p1 p2 by r to the power 4. Force between two dipoles is inversely proportional to r to the power 4. So similarly here force between two magnetic dipoles will also be inversely proportional to r is to power 4. अगर दो मैग्नेट के बीच की डिस्टेंस को डबल करेंगे तो फोर्स 1/16 टाइम्स होगा, right? Yes.
Can you repeat what you just said?
Okay, fine. We did something in the electrostatic when there are two dipoles having dipole moment P1, P2 kept at a distance of r from each other. We derived that formula. These two dipoles exert force on each other, which is given as 6k P1, P2 by r is to power 4. Force between two electric dipoles is inversely proportional to r is to power 4. So same formula we can also use for two bar magnets, short bar magnet, kept at a distance of r from each other. The distance between their center to center is r. This formula can also be written as 6 mu naught by 4 pi m1 m2 divided by r is to power 4. Force between two dipoles. जैसे इलेक्ट्रिक के लिए था, बट अगर सपोज ये पास पास, दिस वाज ओनली व्हेन इट इज क्वाइट फार फ्रॉम ईच अदर, बोथ हैज टू बी शॉर्ट डाइपोल and distance should be quite large as compared to the distance between the length of the magnets. Only then this formula works, right?
Yes, sir.
तो एक बार लास्ट पेज दिखा दो।
हाँ बेटा,
यस सर्टन।
okay, yeah. So अब इसमें तो तब है जब ये दूर है एक दूसरे से, they are quite far from each other. If they are close, then what we do? If they are close, then we have to apply that resultant of four forces. Force between two magnets. और उसके लिए हम फॉर्मूला क्या यूज करेंगे? We will apply two magnetic poles. Like we had the electric force formula according to Coulomb's law. Similarly, we can write this as mu naught by 4 pi Q1 Q2 divided by R square. Now suppose if there is a north pole, south pole, one magnet, and there's another magnet. And no, it's not quite far, so that we cannot use that formula. Now what we do? So there are total 4 formulas. So 4 forces acting. कौन से? ये north को repel कर रहा होगा. So there will be a repulsive force F1. South is repelling south F2. इनकी हम distance निकाल लेंगे because center की distance पता है और magnet की length पता है. Then we will find out the attractive force is south और north के बीच में एक attractive force होगा. इस north और south के बीच में attractive force होगा. So net force on any of the magnet will be the resultant of these 4 forces.
So we'll consider the dipole के जो poles का attraction to be fixed, right?
We'll consider that.
So जो एक dipole है उसका north and south को कुछ consider नहीं करना ना, because it's fixed.
इसी से तो calculate करेगा. Like this is QM1, this is QM2, this is QM1 dash, QM2 dash. Okay, so net force we will calculate between these two north pole, like suppose. So now this north pole will be, let's say the distance between them is R1.
No, so I was talking if there will be any force between QM1 and QM2.
There is no force between.
I was asking if there will be any force between QM1 and QM2.
No.
Okay, sir.
On its own pole, it cannot apply.
All right, sir. Got it.
And so on. Similarly, all 4. The net force between the magnets will be F1 plus F2 minus F3 plus F4. F1 plus F2 minus F3 plus F4. So ये एक तरीका है, बट ऐसे क्वेश्चन थोड़े कम ही है. ऐसे क्वेश्चन ऐसे लग रहा है, ऐसे क्वेश्चन एग्जाम में क्या नहीं आते. It involves a lot of calculation. Right. Next is magnetic field due to a bar magnet. Magnetic field due to a bar magnet. Bar magnet or magnetic dipole. So dipole के लिए जब electric field calculate करते हैं, there were 3 positions: along the axis, axial position; perpendicular direction, equatorial position; and third is general position. In axial position, it was along the line joining those charges. Similarly, along the line joining the poles of a magnet, that will be called axial position. Our distance from the center of magnet, the length of magnet is 2a. So if anyone remember that formula of electric field in the axial position में electric field का without approximation, what was that formula? 1/4 pi epsilon naught 2p times r divided by r square minus a square whole square. Same logic, there is a dipole moment m. R is distance from the
Sir, can you
center.
move to the previous page?
Okay. Done. फोर्स बिटवीन टू मैग्नेटिक डाइपोल्स, मैग्नेट को कैलकुलेट करने के लिए हम सारे पोल्स के बीच में फोर्स निकालते हैं, फिर रिजल्ट। नेक्स्ट इज मैग्नेटिक फील्ड ड्यू टू दी मैग्नेट इन एक्सियल पोजीशन। सो जब हम कंपेयर करेंगे तो एक नॉर्थ पोल को विल कंसीडर लाइक ए पॉजिटिव चार्ज, there will be force a field away from it, and south pole will be considered the negative charge, there will be a field towards it, and the resultant will come out exactly similar to that of electric dipole formula, because the field formula is also same. 1 by 4 pi epsilon naught will be replaced by mu naught by 4 pi, that's it. P will be replaced by M. Correct? This is for a for any dipole. If the dipole is very short, so if it is a short bar magnet, then R is quite larger than A. R square minus A square में हम R square minus A square में हम एड कर देंगे A square को, it become R square. Yes, sorry, it was a parent's call for the admission. So short magnet के लिए क्या होता है? जैसे short dipole के लिए it was inversely proportional to r cube. Likewise, for a short magnet, it will be mu naught by 4 pi 2 m by r cube. Axial position में magnetic field is inversely proportional to r cube, just like the electric field. Direction of magnetic field will be in the same direction as magnetic dipole moment vector, so it will be in the same direction. In the perpendicular to the magnet, that is the equatorial position. Equatorial position means perpendicular to the magnet. There it is. So equatorial position may, if there is no, for any magnet, not just for a short magnet, without approximation, जो formula था. In the case of electric dipole, that was minus of Kp divided by r square plus a square whole to the power 3 by 2. Now there is a magnetic field in opposite direction. This magnetic field equatorial position will be minus of mu naught by 4 pi m divided by r square plus a square whole raised to power 3 by 2. Equatorial position where 2a is the length of the magnet, r is the distance from the point from the center of the magnet. So in this particular case, if magnet is short, r is very, very large as compared to a, we can neglect a square. R square plus a square को हम approximately r square कर लेंगे. So it will become minus mu naught by 4 pi into m divided by r cube. Mu naught by 4 pi m by r cube. Again, it is opposite to the direction of magnetic dipole moment. So सारे के सारे result electric dipole वाले ही हैं. Not just for the field, even for the force and torque, all. एक तीसरा केस किया था हमने at a general position of a dipole. Magnet के center से r distance at an angle theta. Third is in a general position or at a general point. At a general position, like at a distance r from the center at an angle theta. From south pole to north pole, there is a magnetic dipole moment, और ये केवल short के लिए ही है. This formula is only for short dipole. Due to short dipole. So short dipole के लिए r distance हो गया, total length is 2a. हम कैसे करते थे इसको? Dipole moment को इसमें resolve कर लेते हैं. M is resolved as m cos theta and the perpendicular is m sin theta. Due to m cos theta, the magnetic field is in the same direction. क्योंकि इसके लिए axial position हो गया. शॉर्ट डाइपोल को जैसे इलेक्ट्रिक के डाइपोल के केस में किया था, द डाइपोल मोमेंट इज टेकन इनटू टू परपेंडिकुलर कंपोनेंट, म्यू नॉट बाई 4 पाई 2 m cos theta divided by r cube because of this m cos theta component, and because of m sin theta it will be again perpendicular direction. So due to m sin theta the magnetic field will be mu naught by 4 pi m sin theta by r cube. These two are perpendicular to each other, so the net will be resultant. Net magnetic field will be root of B1 square plus B2 square. B1 और B2 का रिजल्टेंट करेंगे तो ये कुछ आ जाता था म्यू नॉट बाई 4 पाई, म्यू नॉट बाई 4 पाई तो कॉमन आ जाएगा, और 2 cos थीटा होल स्क्वायर प्लस साइन स्क्वायर थीटा, सो म्यू नॉट बाई 4 पाई m by r cube सभी में कॉमन है, and this will become 3 cos square theta plus pi. Magnetic field due to a magnet at a general position is mu naught m by 4 pi r cube root of 1 plus 3 cos square theta b1 और b2. और इसमें डायरेक्शन कैसे लिखते थे? Direction was given in terms of this angle phi. So these results are also same, exactly similar to electric dipole. Electric field due to a electric dipole at general position was 1 by 4 pi epsilon naught p by r cube 1 plus 3 cos square theta square root. यहाँ पे p की जगह पे m और 1 by 4 pi epsilon naught को mu naught by 4 pi. डायरेक्शन के लिए we use these two particular angles. या तो हम उस लाइन से रिप्रेजेंट करते हैं, the line joining center of the dipole to that point. उस लाइन से फाई एंगल पे where tan phi is given as tan theta by 2, b2 by b1 कर लिया, म्यू नॉट बाई 4 पाई m by r cube सारा कट जाएगा, बचेगा sin theta by 2 cos theta which is tan theta by 2. Another is next is अगर हम इसको मैग्नेटिक डाइपोल मोमेंट की डायरेक्शन से एंगल लिखते हैं, फ्रॉम द डायरेक्शन ऑफ मैग्नेटिक डाइपोल मोमेंट, तो क्या करना होता है? This angle is theta plus phi. The net magnetic field is at an angle theta plus phi from the magnetic field direction. For that point, so at an angle theta plus phi, at an angle theta plus phi from magnetic dipole moment vector. So theta plus phi from magnetic dipole moment, or it can be written as phi from the line joining their centers. वेरी गुड. सो ये तीन केसेस हो गए मैग्नेटिक फील्ड कैलकुलेट करने के ड्यू टू अ मैग्नेट. अब अगर हम किसी मैग्नेट को चेंज करते हैं इन दी शेप, कैलकुलेट द न्यू डाइपोल मोमेंट. सो नेक्स्ट क्वेश्चन इज फाइंड द डाइपोल मोमेंट, find the magnetic dipole moment of a semicircular magnet, semicircular horseshoe magnet. So initially it was a bar magnet of length L having a dipole moment of m. अभी हमने इसको change कर दिया है to a new shape. This is the new shape of magnetic. This same magnet is changed into a horseshoe magnet. Calculate the new dipole moment if initial dipole moment is, if initial dipole moment is capital M. So अभी जो लेंथ है वो चेंज हो गई. सपोज इट बिकम अ सर्कल ऑफ रेडियस r, तो नॉर्थ पोल और साउथ पोल के बीच की जो मैग्नेटिक लेंथ आएगी दैट विल बी 2r. Initial dipole moment was pole strength into distance. New dipole moment is pole into the shortest distance between them, that is 2r. Small m into 2r, और r को क्या लिख सकते हैं? Since the length L is the semicircle circumference, L is equal to pi r, r will become L by pi. So this become 2 times L by pi. 2 by pi into ml, और ml था initial वाला dipole moment, so that become 2 by pi into m. So डायपोल मोमेंट becomes 2 by pi times initial dipole moment अगर हम किसी स्ट्रेट बार मैग्नेट को चेंज कर देते हैं इन अ सेमी सर्कुलर horseshoe magnet. Right? Okay. Next is magnetic dipole moment in external field. Magnet in external magnetic field. ठीक है. Magnetic field lines क्या होती है? Magnetic field lines are the imaginary hypothetical lines which is used to represent the direction and right. Magnetic field lines are imaginary lines which denote the direction and magnitude. एक तो वो हम लिखते हैं. Second is मैग्नेटिक फील्ड लाइन को यूज करके वी कैन डिटरमाइन दी प्रॉपर्टीज क्या होंगी मैग्नेटिक फील्ड लाइंस की. The properties of magnetic field lines is that the two field lines can never intersect. Magnetic field lines are always in the form of closed loop. Magnetic field lines start from the surface. Magnetic field lines are always in the form of closed loop. Outside is in the form of so north to south की तरफ जो हम move करेंगे it is like the magnetic field starts from the north pole and move toward the south pole. Outside, inside it is. So पहली property तो ये हो गई. It is always in the form of closed loop. It cannot intersect, cannot touch either. जैसे electric field की property थी. The strength of magnetic field will be represented by the density and the closeness of the magnetic field. Closeness of magnetic field line represent the strength of magnetic field. ठीक है. सो ये सारी वही प्रॉपर्टीज जो हम पहले पढ़ चुके. केवल इसमें एक छोटी चीज हमें एक्स्ट्रा समझनी है. वो क्या है? दैट इफ वी अप्लाई द मैग्नेटिक if we apply the if we apply the Gauss law for the magnetic dipole for any magnetic field. Gauss law क्या था? The total number of magnetic field lines passing through a closed surface is equal to 1 by epsilon naught times charge enclosed. बट जब हम मैग्नेटिज्म में गॉस लॉ अप्लाई करेंगे तो ये हमेशा हो जाएगा integration of B dot dA will be equal to 0 for any closed loop. Says the magnetic field lines enter from one side and leave out from the other side. Therefore, the net magnetic flux passing through any closed surface is always will always be 0. जितनी फील्ड लाइन एक साइड से अंदर जाएंगी उतनी ही फील्ड लाइन दूसरी तरफ से बाहर भी निकल जाएंगी. So that also means confirms that magnetic monopoles do not exist. Magnetic monopoles do not exist. Right?
Yes, sir.
Magnetic monopole do not exist, and that is that also confirms that individual poles exist नहीं कर सकते, हमेशा जब भी होंगे, it is always going to be a anywhere. If you consider any loop, एक तरफ से enter, दूसरी तरफ से बाहर. ठीक है, so ये हो गया magnetic field line, magnetic field line की properties, Gauss law for magnetism. Next is magnetic dipole in external field. Magnetic dipole or bar magnet in external field. Magnetic dipole in external field. First, in a uniform magnetic field, अगर हम किसी magnet को रख देते हैं, in a uniform magnetic field, if you put a magnet, magnet की direction से theta angle पर, if we put a magnet, magnetic field is B at an angle theta with respect to the magnetic field direction. तो क्या होगा, north pole पे तो force लगेगा small m is pole strength into B और इस पे opposite direction में. Exactly similar to the electric dipole, the net force is becoming zero. The net force on the net force on this magnet is always zero. But it will provide a torque. If the length of the magnet is L, दोनों के बीच की perpendicular distance आ जाएगी L sin theta. Since they are acting in the opposite direction, there will be a torque acting because of these forces. Force is mv, दोनों के बीच की perpendicular distance आ गई L sin theta. Is equal to small m into L times B sin theta. Small m into L become dipole moment, so that is mb sin theta, जो कि same formula हम derive कर चुके हैं in the case of current carrying loop. तो चाहे वो current carrying loop वाला dipole हो या किसी magnet का dipole, the torque will be mb sin theta. M का formula बस change हो गया. M is NIA for a circular loop and is pole strength into distance for a bar magnet. राइट, mb sin theta को वेक्टर फॉर्म में लिखेंगे तो ये p sin theta जैसे ही हो गया. टॉर्क का फॉर्मूला वहां होता था p क्रॉस e, here it is m cross b. m is the dipole moment and the behavior is exactly same. Theta 0, theta 180 पे torque will be 0, force is already 0. Force is 0 at every point, torque is 0 but torque is 0 when theta is 0 or theta is 180. So put theta 0 when theta is equal to 0 degree और theta is equal to 180 degree. Theta 0 का मतलब magnetic field के parallel, magnet is kept parallel to magnetic field. Theta 180 मतलब opposite direction. पहले केस में थीटा 0 है, so it will be north here and south here. In the direction of external field, force is 0, torque is 0, और थोड़ा सा भी डिस्प्लेस करेंगे अगर हम तो ये वापस अपनी पोजीशन में आ जाएगा. So that is a position of stable equilibrium. किसी भी मैग्नेट को जब भी हम फ्री छोड़ते हैं रोटेट करने के लिए, it always align itself in the direction of external magnetic field. Theta 180 degree is opposite direction. Theta 180 में भी torque 0, force 0. And if we give a small displacement, it does not come back to the initial position, that is unstable equilibrium position. थीटा 0 पे स्टेबल इक्विलिब्रियम, थीटा 180 पे अनस्टेबल इक्विलिब्रियम. स्टेबल पे फोर्स 0, टॉर्क 0, बट थोड़ा सा भी डिस्प्लेस करते हैं तो it does not come back. थीटा 180 से does not come back. थीटा 0 डिग्री से अगर हम थोड़ा भी डिस्प्लेस करके छोड़ते हैं, it come back to the same position, and it also start performing SHM, angular SHM, angular SHM of magnet in external field. एक्सटर्नल फील्ड में हम थोड़ा सा भी डिस्प्लेस उसको कर देते हैं, थोड़ा सा भी रोटेट कर देते हैं, लेट्स से बाय एन एंगल थीटा, तो उसमें जो टॉर्क आएगा, दैट टॉर्क इज अपोजिट टू थीटा, सो इट विल एक्ट लाइक अ रीस्टोरिंग टॉर्क. Restoring torque is mb sin theta, but it is opposite to the direction of the torque. And in this case, that if theta is very small, if theta is very small, तो हम sin theta को थीटा लिख सकते हैं, और torque टॉर्क इज माइनस एम बी साइन थीटा, और थीटा बहुत छोटा है तो हम साइन थीटा को लिख लेते हैं थीटा. टॉर इज इक्वल टू आई अल्फा, थीटा इज वेरी स्मॉल, साइन थीटा बिकम थीटा, अल्फा इज माइनस ऑफ एम बी बाई आई इंटू थीटा. Alpha is minus omega square theta, omega is root of mb by I. I here is moment of inertia. I is moment of inertia. I is moment of inertia. So rod के लिए जैसे ml square by 12 होता था, हम इसको एक rod जैसा, एक thin rod जैसा consider कर सकते हैं. अगर mass है m, length है l, तो we can consider the moment of inertia of a bar magnet as ml square by 12, which is the formula for that of a isolated single rod. Time period is 2 pi root 2 pi by omega, so time period becomes 2 pi under root I by m times v. किसी भी मैग्नेट को एक्सटर्नल मैग्नेटिक फील्ड में थोड़ा सा भी ट्विस्ट करके अगर हम रोटेट करने के लिए छोड़ देते हैं, it start performing SHM and that SHM correct. Okay, that's the time period formula, which is again similar to that of electric dipole. Electric dipole को external field में रखने पे it was 2 pi root I by P. I यहाँ पर moment of inertia था, I यहाँ पर moment of inertia है. P is electric dipole moment, M is magnetic dipole moment, E is electric field, and this that was the torque on a dipole when it is kept in external magnetic field. Formula next was the potential energy of electric dipole. Electric dipole को external field में रखने पे या magnetic dipole को external field में रखने पे, why there is energy? Because there is a work done. Work done किसका? Because of this restoring torque. Force तो है नहीं, force is zero, net force is zero, it cannot do work. The work is done by the torque, और torque के work done का formula होता है tau d theta. The work done by that restoring torque will be work done by the torque will be stored in the form of potential energy of the system. So potential energy of this bar magnet or magnetic dipole in the external field. Potential energy of bar magnet in external field. U is equal to integration of tau d theta, sin theta का integration हो जाएगा minus of cos theta. तो energy का formula minus mv cos theta. Which will become minus m dot b, exactly similar to minus of p dot e or minus p cos theta. जब हम किसी डाइपोल को रोटेट करते हैं from one position to another position, the work done in rotating a dipole is equal to the change in potential energy. Work done in rotating a dipole is equal to change in potential energy, final minus initial. That's minus mv cos theta 2 minus mb cos theta 1. ये माइनस माइनस आ गया प्लस mb cos theta 1 minus cos theta 2. Formula for work done. So the सारे formula same है, exactly similar to electric dipole, and kind of almost 50% of this chapter we have completed. अगर आप next class में वो diamagnetic paramagnetic पढ़ के आ जाते हैं, so we will do quickly some questions on the earth magnetism part. ठीक है, तो ये हमने बार मैग्नेट वाला पार्ट खत्म कर लिया है, which is exactly similar to electric dipole. Now earth magnetism करेंगे हम next class में, and the paramagnetism, diamagnetism and ferromagnetism. So हम numerical वाला part करेंगे, and there are some extra concept which is not in the NCERT, like the oscillation magnetometer, deflection magnetometer, tangent galvanometer. That also we will do after finishing this NCERT portion. ये chapter syllabus से हट तो नहीं गया है?
So it's there, so this.
Huh?
It's there, sir.
Is there? From ICSE it has been removed. Yeah. From ICSE removed. But okay, anyways, this chapter is quite easy, and you just have to learn few theoretical formulas like ferromagnetic example, paramagnetic example, diamagnetic example, and so on. Okay, then we'll continue next class. Tomorrow we will be having questions of that conversion of moving a galvanometer into a meter and तो उसकी practice करना from both from the SL as well as the worksheets that I had sent. Okay, thank you.
Thanks, sir.